Afternoon, gents. Today we're going to look at the solenoids and their operation. I know that many members already have servos operating their points. So why we're looking at solenoids? Well, a number of reasons. One is that they're still in fairly regular use among some home layouts, and probably even more so on club layouts. So it's worth looking at. And some don't have an option. People who've got like Hornby 3-rail systems with the solenoid already built into the point. It's just too much hassle to convert to servos. The other reason is that if you're like me, you like to know how things work. So it's just curiosity to know about it. And thirdly, for those who have solenoids, can we use the usual Merg WASAG motto? Can we do it better and can we do it cheaper? So we're looking at alternatives to what's out there. I'm working on the basis that you all know what a solenoid is. As you can see in the pictures, it's basically just two coils and a slug of metal that can be pulled back and forward. If you energize this coil, then the slug goes in the same direction as the coil that's energized. That's an old Hammond-Morgan type. And then you simply connect to where you want it to be. You can, with a wire, a piano wire, or omega loops and so on. So they're still in production. They're still selling lots of them. So I'm assuming there are quite a number of users out there. That's the most common ones. The Hornby, the Seep, the Pico. On just here, whoops, this one here is basically just a remake of that Hammond and Morgan. Very, very similar, right down to the mechanism here. And that's fairly recently out. So we're looking at a solenoid being two coils that pulls a metal slug back and forward. Sometimes they'll work quite happily on 12 volts. Other times they need a higher voltage to operate. Sometimes even ones that work in 12 volts can be sticky and need a high voltage to make sure they get a good movement, or because of bad wiring, which I'll cover later, then they don't quite get the voltage at the end where they're meant to be. So we'll also look at some resulting wiring and switching issues. The very, very basic wiring, the coils for a solenoid don't care whether they get AC or DC. You can take out the AC at the back of some of the controllers directly and use them to operate points. What you commonly do is you've got two coils. If you press that button, then current flows through that coil. If you press that button, current flows through the other coil. And you can do that multiple times along your layout. And that's fine. But we don't want push buttons necessarily. I mean, we have issues. Why is there not a switch in that picture? Why did they have push buttons? And the answer is that I measured quite accurately the DC resistance of a Pico coil, and it's 4.8 ohms, and the Seep down below at 3.3. So let's assume we just had 12 volts DC, nothing fancier than that, just 12 volts DC. Then the current is going to be 12 over 4.8, 2.5 amps. In other words, there'll be 30 watts. So if you use an off-on switch to operate the coil, you've just turned the coil into a soldering iron or a bar fire. Okay. And down below with the Seep, with a lower resistance, it works out as 3.6 amps or 43 watts. So you have to have passing contacts or stud operation. You can't just use ordinary switches if you're powering it directly from a supply. We have to find a better way of doing it. If we go up to 15 volts, we make the position even worse. We're now at 47 watts for a pico and 55 for a seep. But in many capacitor discharge units, you're talking 20 volts. So they become even worse. They would very, very quickly burn out the wiring of the coil if you had permanent switches rather than passing contact switches. It's for that reason that you'll find people with solenoids in their layout either use a probe hitting a stud in the layout. So you get a control panel, you mount studs on it where the points are, and you have a trailing wire with a probe, and you just touch it on to energize that coil. So you only get a temporary burst of power through the coil. Or up the top, you'll see passing contact switches. So normally it's not, the supply coming in the bottom doesn't go anywhere to the coils. If you throw that same switch all the way to the left, then it has to pass that contact. So on the way past, you get a sudden burst of power to that coil. And suddenly going the other direction, on the way past to get to the right-hand extreme, you make a contact with the other coil. And in that way, we make sure that we don't burn out the coils, always assuming that the switches don't jam or stick in the contact position. Having said that, they're effective, but they're expensive. There's the Hornby. Hornby's own website are selling it at $11.99. The Pico version's a bit cheaper. You're still talking about £8 per point, which is very expensive if you've got a largest layout, say with 40 points. 40 times 12 is an awful lot of money. You know? Is there a better way? Well, this takes us on to the issue before I look at it of the wiring. You'll see on the right-hand side, there's the two coils of the solenoid. They're common together at one point and go back either to the power supply or maybe through a CDU. And you're passing contact switch. By the way, that's the range I found for sale at. £12 on the Hornby website, as low as £9 or up to 16. Anyway, you need 3 wires then. One for the common and one that goes to either coil. So that dotted line represents for every single point, you have to run 3 wires between the switch and the solenoid itself, raising all kind of issues about voltage drop, bad contacts and so on if you've got a large layout. That's what it may look like. If we then have multiple points, then for every point you need to have 3 wires. In practice, these are probably all the same CDU. You've got one CDU near the control panel where the switches are, and then 3 wires from that to every single solenoid. You can save a little bit of wiring if you common up the commons of the coils themselves. Despite that, we're looking at lots of wiring, not only that, but wiring that's having high current. Because we're talking about a high voltage, high current surge for a short time. And I've put on there 1 ohm, just as a kind of example. What would happen if you had 1 ohm of resistance, either because the wiring you've used is too thin, or maybe you've got a bad, not so good contact somewhere in the switch or in some joint or some terminal block or whatever. Doesn't sound much, and you can end up with much more than that, especially with corrosion and so on. Even 1 ohm. If you look back earlier, we said there was things like 3 or 4 amps of a pulse. Then by Ohm's law, that would mean that bit of wire would be dropping 3 or 4 volts. So if you've got 12 volt supply feeding it, you might only be getting 9 or even less by the time it gets to the coil. And then you wonder why the metal slug is a bit sluggish and moving back and forward. It's not as crisp as it should be. And that's why, again, people then say, well, we'll compensate by having a higher voltage from the capacitor discharge unit. We won't rely on the 12 volts. Still lots of wiring. Now, can we improve on that? Well, let's start by looking at a very basic capacitor discharge unit. This one is assuming that we have an AC supply and we're powering it from the back of a controller. We have to rectify it and then charge up a capacitor and then briefly discharge that high voltage through one of the coils. The higher the value of the reservoir capacitor, the more power you can store to zap through the coil. We've got a resistor in series there for a couple of reasons. One is, if it wasn't there and the capacitor was fully discharged, and then we suddenly apply 20 volts to it, because 15 volts once rectified is approximately 20 volts. 20 volts into a discharged electrolytic could easily just blow the electrolytic. So we put a resistor there which cuts down the current flow. So if you looked at what's happening across this capacitor, the voltage slowly charges up. So there's no sudden surge into the electrolytic. So if we didn't need the diodes, we've got a CDU we can build with 2 components, pennies. That's what it looks like when you first switch on. You're starting to charge up the voltage. The minute you press the button, sudden discharge. And it'll stay discharged, that capacitor will stay discharged as long as you hold the button down. The minute you release the button or the prod or whatever, the passing switch, then the voltage builds up again until the next time that you press the button. And because you've got a resistor there, if that switch happened to jam, then you'd be drawing current. If that wasn't there, you'd be drawing a very high current all the time, 4 amps all the time through that coil. By putting in that resistor, then we limit 150 ohm resistor, a few ohms for the coil, results in only 130 milliamps. Still too high, but only giving you roughly 1 or 2 watts of power through the coil. So it prevents damage to the coil. So it's got 2 jobs: prevent damage in the case of a jammed switch, and make sure you slowly charge it as not to damage the electrolytic. When I say slowly charge it, I'm talking in relative terms. So I've got one, we can actually see it. There's one there, just using the old Hammond Morgan. 2 components, big electrolytic, a resistor. This is the circuit here. Just press the button, discharge the capacitor. It's now charging, discharging. It's charging, discharging, and that's fine. But if I try to do it too quickly, you can see that it doesn't function because we're trying to discharge it before it's time to properly charge. If I leave it about 1 second, it's got time to charge. If I try to do it too quickly, it won't operate. Having said that, if you're happy to have a 1 second delay between changing each point in the layout, you can build your own CDU for 30 pence or something. So that's what we can do for almost nothing. Now, in terms of switching for solenoids, there's a set of Hornby passing contact switches that I showed you earlier on, assembled into a bank. And some people really enjoy that because it reminds them of the lever frame inside a signal box. This particular guy has had to color code them to remind them, because if you've got 10 or 20 passing contact switches in a row, what the heck do they all do? You have to label them in some way unless you've got a great memory. And that's fine if you like that kind of thing. But lots of people prefer to have the switches already mounted in their control panel. That's my control panel I've got, and you'll see all I've got are perfectly ordinary off-on switches. I want to switch them where the points are in my layout as opposed to on a bank of passing contacts. Also means that it's a toggle switch, so it tells me which way the point's set. The switch is up that way, the point's set that way. The switch is set that way, the point's set that way. So what we'd like to have happen is have CDUs that we can operate through switches on the control panel, if that's your preference. So how do we go about that? Well, starting point, Brendan kindly loaned me a gauge master to have a look at, and it's fortuitous because one of the members that's on happened to email to say, how does it work? And the answer, Campbell, is what I did when I got it. That's the underside. The top, you can see the components, and what I had to do is try and work out what was connecting to what underneath. It's not a particularly hard layout, and that's what it looked like. Handful of components, and once I worked out what soldered where, I can work out a circuit diagram, and that's all it's to it. So on the input, you have your 20 volts, say, for talk's sake. It's got a diode there in case you happen to put an AC in. We've got a power transistor that can charge up the capacitors, and then the output comes out the other side. How does that work? Well, when you first switch on, that's what happens. Those who were at the Electronics 2 course, I remember we spoke about NPNs and PNPs. This one is an NPN. In other words, if you put a positive on there, it will allow current to conduct. And we have put a positive on it via this. So this is now conducting. In other words, it's letting current flow into these and charge these capacitors. They're in parallel. You could easily have fitted one 2000 microfarad, but they've put in two 1000. I don't know whether that's for cheapness or whatever. So when you've not pressed any buttons to operate any switches, you're charging up these two capacitors. And then the next step is when you actually want to operate a point, you can forget about this side. Now there's a path to discharge through the coil. So you get a sudden discharge, 20 volts at high current going through the coil. Zap. If you kept the switch pressed down, then what happens is that's now discharged. We can forget about all that. The coil is now putting a very low resistance between here and 0. So it biases off the transistor. If we didn't bias it off, if it was still conducting, then once again, we'd be trying to punch 4 amps through that transistor, through the coil. So it acts as a cutoff. And instead, we have a 47 ohm in series with the coil. Once again, current limiting. And then we still have to put it through some switch. I should mention the diode we have up there is there to, we're going to be switching coils. And therefore, if the switch does jam or you keep the button pressed too long, you might be faced with a back EMF, a reverse voltage, which would come in and destroy the circuit. So that's there to prevent any back EMF. So we have that circuit at that end going to be in your control panel, say, and at this end of the layout, we've got the coils. We still need 3 wires between them. So we've still got to energize one coil or the other, and we still require to have a return leg. But the difference is now, this doesn't have to be a passing contact switch. Because we know that when we make a contact, it prevents overcurrent. That's what the commercial one looks like. And there's a 71p version that does the same, in fact better, because instead of fitting 1,000 microfarads, I fitted a 3,300 microfarads. So it's got greater capacitance, with a greater storage capability, and costs a fraction of the price if you're willing to build your own and a bit of Euroboard. And I can show that in practice. Just give me a second. Right. What we have is the circuit. We have the little module up here. I've put 16 volts on here. I've still got 3 wires, 2 coming from the switch. You can see them in yellow, and there's a copper link there for the common. Still 3 wires, so I haven't solved any wiring issues. But the switch we're using is a center off switch. So you throw it one way to go one direction. There's a midpoint, other direction, midpoint, other direction. So we're now able to use this circuit, no saving in wiring, but we can use a perfectly ordinary switch, a center pole double throw, center off switch, in place of a passing contact. You could still use a passing contact switch, but why pay 12 quid when you can pay 25 pence? So that's the gauge master. Somebody asked me, can I do the same for the Pico? But I don't have a Pico to take the bits to have a look at. So instead, we'll have a look at Merck's own, which is a really good design, in my opinion. The PD3. Quite expensive, but once again, got a solution for that, haven't we? It handles 2 different solenoids. So it's really 2 on the one board. How does it work? Well, we won't look at all of that, but some you'll have spotted right away is it's 2 of the same. The top circuit is the same as the bottom circuit. So we can clean that up and say, that's approximately what we're looking at. The price you pay for this one is that you have a capacitor for each coil. And the switching is done by a relay. So everything you see within that box is the kit. You have an external switch How does it work? Well, let's assume for a minute that C1 and C2 are already charged. And then you throw the switch, or you let the relay not be operated, which means that the contact drops to that position. In that situation, that charged capacitor is going to zap its way through the coil and operate the coil. Yep. If we then operate the relay, after it's exhausted its charge on the capacitor, what's going to happen is, once again, we're going to charge up the other capacitor through that same coil. Remember, coil A has got a very low resistance, a few ohms. Combine that with R1, and that's your charging circuit for C2. So we're doing two things at once. We're discharging C1 through the coil to make it operate, and we're using that same circuit to charge up the second capacitor. The switch is just a simple on-off switch in this case, nothing fancy at all, just an ordinary off-on switch. So we throw that switch, the relay operates, and now the contact goes to the other position and does the same thing in reverse. It'll discharge this C2 through coil B this time, and then when that's done, it'll then start charging up C1 again through here, here. So we've managed to get a position where there are still 3 wires at the end, but there's no reason why this CDU now can't be right next to the point. And we only need 1 wire to go to it. That's the second one getting charged up. Like I said, everything's inside that one case. Why not have that sitting right next to the point, especially if it can be cheap? Instead of having one common CDU sitting in your control panel with lots of wires, with lots of thick wires to make sure you don't have losses, we can in fact have this as a module sitting right next to the coils. And then all we need is, we've got a common 0 anyway, everybody's layout's got a common 0 bus. We only need 1 wire from the switch on the control panel to the module. Like that. Assuming we've now got we're high supply to all of these and we're 0 volts, all we need is another single pole, single throw switch that will energize the relay that's in there. So it's only 1 wire to each module now. And these are ordinary switches on the control panel. It makes life so much simpler and more intuitive, in my opinion. And on top of that, because there's a relay already in there, that relay is a double pole, double throw. It's not just switching the coils, it's also got a spare pair of a changeover. And if that's right next to the point, what have you got? You can now do frog switching right at the point. This technology is sitting right next to the point. Great design, in my opinion. That's what it looks like, but that could be sitting, say, at the point end. That's all it needs. Not a lot. That's for building 1. So the mere kit at £8 odd is for 2. If you want to build 1, a bit of aero board, then you need a relay, a couple of big charging capacitors, a couple of 3 diodes and so on, a bit of aero board, and the total cost is £1.34. So at that kind of price, you can afford to have 1 of these right at each point to give you frog switching facility as well as point change facility. And of course, that one wire that's coming back from that module all the way back to the control panel could be a thin wire. It's not handling high current at all. It's a signal wire. It's not really a high current wire. And I think we can, there it's there. Let me show you that one. But the point to show you here is, assuming we've already got power at the point end, it's only one single wire that we require, thin wire between the switch and the module itself. And the last thing that I wanted to quickly look at is, we've looked at so far at using switching, ordinary switches or center off switches or passing contact switches or prods. We can operate solenoids other ways. I'm showing you the prototype of Charlie. He's building an automatic shuffler where he's got a loop with various sidings on it and a loco in each one. And this pick chip here, whoops, that pick chip here is going to open one of the sidings, operate a point, and out will come that loco, come back round, stop, and then that circuit will switch to the next one, then the next one, then the next one. So there are 4 locos, one at a time, going round in that loop, which would be ideal for an exhibition, of course, all automatic. The relays are not on that board, but you'll see at the end, we're operating the solenoids this time from MOSFETs, large power MOSFETs. So the pick switches on the MOSFET, and the MOSFET will give you the power switching to the coils themselves. Something like that. That you can control automatically which points operate when. In Charlie's case, we're expecting that Charlie, when he's finished this, will show it to us all working. He's made that commitment and we're holding to it. But what he's got here are totties to know when the train has finished doing its rounds to track 1, it'll then switch to track 2. So we're using inputs here from train detectors, and they in turn have an influence over the which points get switched and also which relays get switched. But it could be anything. So we're operating points via an Arduino or via a PIC, or maybe sometimes even direct from a totty. So we've got lots of life still in solenoids for those who are still using them.